Good morning, everyone. We'll just wait a couple of seconds to allow participants to get into the meeting, and we'll start our presentation in just a few seconds. Thanks for your patience. All right, so let's begin. Hello, everyone, and welcome to today's session. I am Marisa Fraser Morera with Pion, and I will be moderating today's event. In today's session, we will be conducting a live demo and demonstrate how Pion envisions in vitro assay data processing through our user-friendly software platform, Pion Predictor, and will be presented by Balint Cinco. Balint earned his Master's of Science in Pharmacy from Semmelweis University in 2007, followed by a PhD in Pharmaceutical Sciences in 2012. During his PhD studies, he developed a skin penetration model that has since been licensed and commercialized by Pion. Today, Balint leads Pion's development team, focusing his research on the impact of formulations on intestinal and skin absorption. With over 25 research articles published in peer-reviewed journals and co-authored book chapter, Balint is recognized for his contributions in the field, and he also serves as an industrial consultant for multiple PhD students and institutions, including University College London, Semmelweis University, and Budapest University of Technology and Economics. Additionally, he holds an honorary associate professorship at Semmelweis University. Now, before I hand things over to Balint, I just would like to briefly cover a few housekeeping details. If you need technical assistance during the webinar, please send your query to the host with the chat function. You are also encouraged to contribute to the success of these webinars by asking questions at any time during the presentation through the Q&A box on your screen. Our speaker will answer them at the end of the presentation, and any questions that we don't get to today will be answered by email after the event. Lastly, a recorded version of this webinar will be available on our website within 24 hours, and you will also receive an email with a link to the recording also within 24 hours. So now, without further ado, I will hand things over to Balint. Balint, over to you.
Thank you very much, Marisa, and welcome everybody to this session where I will show you how the Predictor software can help you to transform in vitro data, mainly collected by our Rainbow and AU Pro platform, into in vivo related parameters, predictions, and information. So as a short agenda, I will start with an introduction to the Predictor software in general, and then I have 4 case studies, and through those 4 case studies, I would like to guide you through the main features and benefits of the Predictor software platform. So in the meantime, I will turn off the camera if you don't mind. So the foundation of Pion's fiber optic product line is, as you know, the Rainbow hardware, which is an in-situ UV spectrometer, and the AU Pro software that was designed to drive that or to control that system. This system, this combination, is used in numerous applications around dissolution assays or supersaturation precipitation kinetic studies, or dissolution permeation or flux experiments to study excipient effect, or to compare finished dosage forms. AU Pro software has been mainly developed to drive the actual hardware and to collect data, and then for the initial data processing, which means that AU Pro has superb capabilities to convert the UV absorption data into time versus concentration profiles. We have numerous ways to do this conversion and to deal with turbidity and to deal with any additional factors that can impact the absorption spectrum, and we can determine the actual concentration data in every 5 seconds, basically. However, when we talk about further processing this information or these results and taking these concentration profiles and converting them into dissolution kinetic information or precipitation kinetics or flux calculations, then AU-Pro had some limitations. That's why we decided to develop a software platform where we are focused on taking these data, taking these time versus concentration profiles, and doing all sorts of curve fitting and calculations and predictions to actually provide results and information for the users. The Predictor software platform actually has 2 modules. The data module is the foundation of the software, and that module deals with all the data management. It deals with all the dissolution and flux curve fitting and data analysis, and also all the reporting capabilities. I will show a few examples of these during the demo. And the fractional absorb module basically sits on top of the data module, and that module is responsible for flux data treatment mainly, and to convert this flux data to in vivo absorption rate prediction or effective in vivo effective permeability predictions, or particle drift effect modeling, BCS or fractional absorb classification system characterization, and also determination of the fractional absorb rate limiting step. Talking a little more about the data module. So this was designed to give complete freedom to combine and analyze and average dissolution and flux data sets. So you can take multiple channel data from different AU-Pro experiments and then combine them into one set, treat them as like one data set, do all the curve fitting, do all the data analysis as a coherent data set. You can create reports fast in Excel, PDF, or document format. You can include or exclude data points on the interface, and you can freely change the units for each parameter, either on the graphical interface or in the properties table as well. And you can do like a standard click and drag zoom, as you would expect from any modern software. On the right-hand side, I just gave you a list of the type of curve fitting and the parameters that you get out of those as an example. So if you talk about the dissolution data, then we can do a dissolution or powder dissolution assays, and in that case, we can report solubility, dissolution rate, intrinsic dissolution rate, or estimated particle size. You can analyze this dissolution data, or just like just normal dissolution data where we report dissolution rate and API solubility. You can do basic data processing, average concentration determination, or area under the curve calculations. You can also analyze supersaturation precipitation studies. You can get precipitation rate or induction time, and of course you can analyze flux data as well to get the actual flux and the lifetime. If you talk about the fractional absorb module, then that module was designed to take primarily the flux data, the acceptor side of the flux experiment, and convert that to in vivo related predictions. To do that, we have utilized the GUT framework, so the Gastrointestinal Unified Theoretical Framework that was developed by Kiyohiko Shugano, and basically utilizing the fundamental principles of that framework, we take our in vitro flux results. We are considering the differences between the key differences between our membrane and the intestinal membrane, and we are scaling the flux to that. We are calculating the available or accessible surface area in vivo, and we are considering that. Also the transit time, and we are mathematically considering the dose clearance as well. I will show you an example on that. On the right-hand side, you can see where we are with the validation of the model. On the top graph, we have a comparison of 17 marketed drug products, where we calculated we predicted the fraction absorbed percent, and we compared that to the in vivo fraction absorbed percent. And on the bottom one, these are pure APIs, where we calculated the effective permeability and compared it to the in vivo human genome effective permeabilities. So, because I have 4 examples, I would like to dive into the first one, and this is going to be around the dissolution curve fitting. And the project was to measure the intrinsic dissolution rate and the solubility of dipyridamole and to estimate the particle radius. So simple experiments were run on the microdis platform at a pH 6.5 phosphate buffer, and I'm going to process the data. So for that, I will swap to AU Pro, and while I'm doing that, we would like to pose a couple questions or polls, which my colleague will do, and I hope you can give us some feedback based on that. So I will wait a second, and probably in the meantime, I'm just going to open the right AU Pro data file. Yes. So the AU Pro data file is open. It's actually unprocessed, so I will just click the automated data processing and let the system to do the data processing. And basically that sets the right evaluation parameters, and I get the dissolution data. So once I'm sure that the time versus concentration profiles are accurate, then I just need to go to the file menu and click export to Predictor. And on this small dialog, I can select which channels I want to export or which component if it's a multi-component analysis. And by clicking export, then the export is successfully happening, and that's it. That's all we need to do in AU Pro. So now I will move over to Predictor. And yeah, so this is the main interface of Predictor. And today we will focus on these 4 toolbar buttons, which basically represent the 4 main functionality of the software. And we will start with the flux dissolution view, and I will show how to process this data. So here on the top, I have a button to add data. And when I click that, then I have this import dialog, where basically I can select which data I would like to combine. On the left, I can select the folder where I have the exported data. That's already selected. And basically I can just select channel by channel which data is that I want to combine. If I click on one of these data, then in the right bottom corner, I get all the assay parameters, so I can actually be sure that, yes, this is what I want to add to my data set, and I get a quick preview as well. So if I click the plus, then with that, I'm just adding it to the data set, and by clicking import, data is already imported to the interface. So in the interface is split into 3 portions. The left-hand side is the properties table, the middle is the graphical representation of the data, and the right-hand side is the table format. I will hide this table format for now. So in the properties, you can see that a lot of the data is already populated because we are taking all this data from AU Pro. And here I can just rename or give a name to the whole data set. I will call this DPDS dipyridamole, and maybe just call this the round 1 that I've imported. And you can see a yellow highlight here. These are the parameters that are considered for this particular calculation. So what calculation are we going to apply? It depends on the type. If I open up this type, this is where you can select the type of the assay, and basically that the type of the assay will determine the type of the calculation that we are using. In this case, this is a powder dissolution assay, which means that we had all the parameters set for all the parameters followed for this experiment, that we can actually do an IDR estimation as well based on a powder dissolution assay. So now that I've selected, the only thing I need to do is to click the range button in the left top corner. And with that, I immediately have these time markers that I can set, and you can see the fitted data and the results already showing up on the left bottom on the properties table. So solubility is reported, dissolution rate, intrinsic dissolution rate, the effective particle radius as well. And you can, of course, set the time markers here in the assay range, or you can just move these bars and click, and all these parameters are dynamically recalculated. What you can see on this actual data, that the fitted curve doesn't follow very well the actual data points. So what I will try to do, so just remember that the estimated particle radius was 18 or almost 19 micrometer. So I will try to move this and basically focus this curve fitting more on the initial portion of the curve. And you can see that I've achieved a much better fit here. And if I click the range button again, then I can add a second range. And I will just move this marker here. And basically the second range, this orange range, it's the data or the fitting is focused on the later stage of the data. So if I hide this assay properties section, then you can see all the data now here for the first range and for the second range. And what we can suspect in this case, that this actual powder sample had two separate populations of particles, potentially, one being smaller than the 18 micrometer that we initially predicted, and this being 14 or 15, and that resulted in a faster initial dissolution. And then we can have a particle population that is much larger, closer to 50 micrometer, and that would result in the later stage slower dissolution. You can also see that the solubility estimation is actually seems to be more accurate with this approach. So this was only the analysis of one data set, but if I click Add Data again, and I basically just select the remainder of the data or the remainder of the channels, basically, and import those as well, then immediately you have all these processing done for all the channels, and you get automatically a statistics tab where all these parameters that were calculated channel by channel, those are all averaged, and you get variation as well. And also in the table, you get the average concentrations and the calculated standard deviation for all these data. So it's a really quick and easy way to combine data sets and get these average profiles. So this was the first example on the dissolution curve analysis. And I will move to the next example or the next case study. And this is already around flux and around dissolution permeation experiments. And the project is the absorption rate prediction of a marketed drug product, Abilify, and this studying the impact of dose clearance. So to be able to do this absorption prediction, we need to run flux experiments in biorelevant conditions, as biorelevant as possible in our systems. So basically, in this specific case, we have used the microflux setup, and we did an SGF to FASIV media conversion assay. It's also very important to have a biorelevant dose to volume ratio. So in case of microflux, that means that we have scaled down the dose to the 20 milliliter media volume. You can, of course, achieve that with the MiniFlux platform as well, with a whole tablet and the 250 milliliters in the donor side, or the same in the BioFlux platform. And technically, it is achievable in the MacroFlux platform as well, even though the volumes are much larger. So potentially, you would need to use multiple dosages to achieve the relevant dose-to-volume ratio. So I will switch back to Predictor, and I will move to this next type of view, and this is a new fraction absorbed prediction view. So as you can see, the interface is more or less the same, although the graphical portion is actually split, because in the top we will see the flux data that we are importing, and in the bottom we will get the absorption prediction as a function of time. So again, I click this add data, and in this case I have the Abilify, the experimental data are already exported into the right format, so they're already here. And so these are the dissolution data, and channel 4, 5, and 6 were the flux data. To keep the interface cleaner, I will only process a single replicate in this case. So I just selected the flux data and clicked import, and the flux data is imported with the table format as well, which I'm going to hide again. Yes, so I just give it a name, Abilify, and we can call this round 1. So again, all these data, all these parameters are imported from the AU-Pro assay, including the membrane surface area as well. One thing to pay attention to, that the biorelevant media, because we have imported the acceptor data, the donor data, the dissolution side is not included in the import. So we should select what type of biorelevant media we have used, or if we have used any kind of biorelevant media. In this case, we did. We had FASIF, and we have a whole new set of parameters here below, and these are the parameters that are going to be used for the absorption prediction. So the first and probably the most important parameter is the species. So currently we have human is the default, but you can actually set up your own properties as well. I will just quickly go to this toolbar button, which will bring up the species dialog. And this is the dialog where you can actually define the properties, sorry, the properties of the human. So these are fairly standard physiological properties: radius of intestine, transit time, volume, the degree of flatness, and the Willi parameters, water layer thickness. And if you want to set up your own species for rat, for example, or a different type of human with a different transit time, then it is easily doable. So we will just go with normal human. Here we can set the dose. In case of Abilify, it's 15 milligram. Even though if you don't set the dose or set just an arbitrary number to the dose, it will only impact the fraction absorbed, the percent of fraction absorbed, and not the actual absorption rate predictions. The dissolution media concentration, that is also needed to be able to calculate a permeability from this flux profile. So we need to enter the donor side concentration that relates to the same or similar time interval where we have the highest flux on the flux curve. And we have previously looked at that in this case it's 70 microgram per mil. The apparent permeability will be calculated as soon as I add the time markers, which I'm going to do in a second. But before that, an important step is to set the flux assay type. In this case, it's microflux. So this determines the hydrodynamics of the system, and this will help us to understand what type of an unstable water layer you had in your system as a function of the storing speed. Biomass cell term, this is needed for special medium permeable cases, and I'm not going to explain that in detail today. Solubility in the dissolution media, that's also something that should be entered. And this is, again, so it's not the concentration, not the highest concentration in the dissolution media, it's the actual solubility in that media, which needs to be measured in many cases as a separate dissolution assay. And I will enter that as 80 microgram per mil. KDs that kind of relates to that experiment or can relate to that experiment. This is the dissolution rate constant for the sample. And if we want to, so in this case, the Abilify will dissolve in the SGF phase, basically to 100%, and therefore the KDs in this case is not relevant. So we can set it to one per minute, and that will give a sufficiently high dissolution rate that the dissolution rate is not going to be considered as a rate limiting step. Particle drift effect is, we're not going to use that in this example because it's not relevant here. So the only thing that's left is basically setting up the time markers. What does this mean? T0. T0 is when the intestinal section of the flux experiment started. So as I said, we did an SGF to FASIV media conversion assay, and we did the media conversion at 30 minutes. So I just add 30 minutes because that's where the intestinal section of the flux assay started. Then for linear one, I need to add the time when the flux became linear after this initial ramp up phase, and I will just add 70 minutes. And as you can see in this case, after a certain time, the flux is non-linear, so I can just add another time marker, like roughly from like 100 minutes. It's not linear anymore, so it will do a polynomial fit. So now if you look at this fitted line, that's actually been fitted on the flux curve, and if there is a good match, then we are actually modeling our flux profile appropriately, and this model data is used for the absorption prediction. But as soon as I've added these markers, you can see that the apparent permeability is calculated, and the results show up. The permeability level being high, and the maximum fraction absorbed is 91% here at the end. Absorption rate is calculated, the total mass absorbed as 13.6 milligram, and the in vivo effective permeability is also provided. Yes, so running the calculation itself is relatively simple. These couple of parameters needs to be added, and some of them needs to be measured in a dissolution assay. The one thing that I wanted to emphasize is the dose clearance. So if you look at the flux profile, although it has a little bit of a slowdown towards the end, there is a slight bend in the curve. The actual bend in the absorption rate is much bigger than here. Why is that? Because as we are having a bigger and bigger portion of the dose being absorbed, then we have a lower and lower donor site concentration, and that means that the flux is actually also decreasing. This effect is not happening in our in vitro setup because of one of the limitations of the in vitro flux assay is that the membrane area is relatively small, and therefore it cannot absorb, it cannot clear that much of a dose from the donor side, and therefore we see that the flux is relatively high throughout the whole duration of the experiment, while this wouldn't be the case in vivo, because with the dose clearance we have a constantly slowing flux. So this is represented here, and it's accounted for in the modeling. Under the graph, I can actually change this and look at the in vivo absorption rate, and then you will see that the absorption rate is is constantly slowing down as a function of the dose being cleared from the site of absorption. Okay, so we have a poll question that relates to this topic as well. So Marisa, if you could activate that while I'm switching back to the presentation. Yes, so the next case study, or before the next case study, I would like to talk a little bit about the particle drifting effect. Although I'm not going to go into too much details because a couple months ago we had a great webinar with great speakers, with Kyo Shugano, with Na Lee, Patrick Shinko, and Carl Box. So in that webinar or workshop, we have basically covered all the details and aspects of particle drifting effect. So just as a quick summary, in case of unstable water limited compounds, when the rate limiting step of the absorption is not the permeation through the membrane, but actually the diffusion through the membrane surface or the diffusion through the unstable water layer. So in these specific cases, if there are small enough particles, nanoparticles, or drug-rich colloids, they can actually diffuse into the unstable water layer, and with that, they will reduce the effective thickness of the unstable water layer, and through that, they will increase the absorption rate. So this is the primary effect that we are trying to study in this example. So the project is the absorption rate prediction of nanoparticle formulations of nabumeton and understanding the particle drifting effect. We should talk a little bit about the assay design to start with, because in this case, one flux assay is not enough. We need to understand the impact of particles on flux, and therefore we need to run at a minimum of 4 experiments. One experiment is suggested when the dose is roughly at solubility or close to solubility. So in this case, we don't have any particles, but we are measuring the maximum flux provided by the dissolved drug. And we need to run at least 3 experiments with the dose being above the solubility. So in these experiments, we have various amounts of undissolved particles, and we are measuring their impact on the absorption. So I'm going to switch to Predictor again, and we'll show how this can be done. And for that, I will use the particle drift effect modeling view, which again has more or less the same interface again, but now the properties view is split as well. What we need to do is that in the top compartment, we need to import the donor side, so the dissolution side of the flux experiment, and in the bottom side, the relating flux experiment. And having those 2 information together, we will calculate one data point for the PD modeling. So we will need to import every single flux experiment data, and that's going to be used for the prediction. So how this goes is I will just click Add Data again. And that will bring me to this section, but I will go to a different folder. For example, so this was the 250 milligram commercial product where we run 3 replicates. And this is the donor side of replicate 1. And this is the acceptor side of replicate 1. And I'm going to add those to the view and click Import. So in the top, we have the donor data, which is pretty much a very quick dissolution and a more or less stable concentration. And on the bottom, we have a constant flux. All I need to do is to use these time markers again and select a range where the dissolution or where the concentration is stable. And here we are calculating the average concentration. That's the information that we need from the donor data. And from the flux data, we just need to find the portion of the curve that provides the highest flux. So in this case, probably that's a relevant time marker selection, and the flux is calculated. So if I keep on adding data like that, like channel 2 and or 3 and 4 as the second replicate, then I basically I need to do or repeat the same activity, find the right section, and get these data points. So these are now added together. So I will now open up the PDE when all the 12 channels have been imported, and it's this one. So as you can see, all these views that we see, those can be saved and then later on opened. So I'm just opening up this when basically every single pair have been imported. And if I go to the statistics tab, the last tab, this is where we get the particle drifting effect related parameters. So in the top, these are the flux data, and please disregard this linear fitting. Originally, we had a linear modeling and an exponential modeling approach. And this still reflects here the linear modeling, even though we will go only with the exponential approach because that provides a more accurate data. That provides a more accurate consideration of the particle drift effect. So basically, what we have here in the bottom curve is the undissolved dose concentration or the PD flux, so the flux provided by the particles as a function of the undissolved dose concentration, and we are calculating the required parameters based on this curve fitting. So we get a P particle, which is essentially the apparent unstable layer permeability for the particles. We are calculating a J max, which is the maximum flux that the particles can provide, and we have the JS, which is the maximum flux that the dissolved API can provide. So with that, we have these key parameters that we can use in a fraction absorbed prediction. So how does that work? I'm going to open up the nalbuphine example, the 1000 milligram dosage. And basically, we need to do we need to run the same absorption rate prediction as we did for Abilify. There is no difference there, adding these parameters, then getting all these human parameters, flux assay type, all this is the same, except except that for the PD modeling, we are enabling it. And then when we are enabling it, we can basically click here and we can select the PD modeling, which we already did. Oops, I rewrote this number. So and basically we just import these P particle, JMX, JS parameters, and all this is applied and considered in the absorption prediction. To see the impact, I will now disable the particle drift effect modeling, and you can see that the orange curve dropped dramatically. So it's down at like 16% fraction absorbed. So the total mass absorbed is like 160 milligram. And if I go back and enable the particle drift effect, then looking at the same numbers, it's 96%, and the total mass absorbed is 969 milligrams. So considering this particle drifting effect has a huge impact on the actual prediction. Why is that? So partially because the particles can contribute to the permeation significantly, and also because the particles can like diffuse slower, but they can diffuse in the entire unstable layer system, and therefore they can take advantage of a much bigger surface area than if you only have a highly permeable compound. So therefore, the particles can actually increase our prediction dramatically, even if they are only providing a fairly small flux increase. So if you look at the this data. It's like barely a twofold increase with this dose. So here, this was a dose at the saturation, and this was a dose slightly above. And you can see that the flux is merely double, while in here, if we consider the particle drift factor down, the change is like 5x or even more. So we have one last question, which I asked my colleagues to put up while I'm switching back to the last example that I have for today. And this last example is going to be this last example is going to be basically the assessment of how we can take this data even further, or how we can provide further information and further help and support for the formulators. So the project is assessing the fraction absorb classification system and the rate limiting step of absorption of marketed drug products. In this case, it's itraconazole solution and itaconazole or Sporonox solution versus Sporonox capsule. Sorry, the BCS classification is wrong. It's BCS class 2, actually. So just very briefly on the fraction absorb classification system. So this was again developed by Kiyohiko Shugano, and the whole concept is to determine the rate limiting step of absorption using this model concept, and figure out if the dissolution rate is the one that's limiting the absorption process, or permeability, or solubility. And solubility can be solubility multi-water layer permeability, or solubility epithelial membrane permeability rate limitation. So with that, he has proposed a whole system that guides the formulators to find out the best strategy to improve the absorption, depending on what the rate limiting step is. And also it gives a guidance of how the food effect or what food effect can be expected, for example. So this is what we will provide in the Predictor platform as well. And I switch back to Predictor. And in this case, I will open up the two already processed data, one for itraconazole capsule and the other one for itraconazole solution. So if I'm on the itraconazole capsule absorption prediction, then I can open up a relating view to this fraction absorb prediction, and that will take all the data from this prediction. So now if this is the active view or active profile, then I can go to this icon and open up a new fraction absorb rate limiting step, or FARS view. And that will bring up this screen. So what we have here, on the left-hand side, we have a bunch of calculated parameters. So these are actually taken from the actual prediction. So the maximum fraction absorbed, the in vivo absorption rate, total mass absorbed, these are all taken from the absorption rate prediction view or data processing. So based on these data, we are calculating permeability number, dose number, dissolution number, and dose number. These are dimensionless numbers that kind of reflect or describe these processes. Based on these, we calculate a fraction absorbed steady state. So this is not the same fraction absorbed as the one that we calculate in the original view, but it's more on the assumption when the dissolution and the permeation are in equilibrium, basically. And we also provide a BCS class prediction, and also a fraction absorbed rate limiting step prediction. So in this case, we say that the absorption of this compound from this formulation is a solubility of the water layer permeability limited case. So the other thing I can do, so this, we have a 3D plot here where we have the y-axis is the fraction absorbed steady state, so basically an estimation of the fraction absorbed percent, and we have we show that on the 3D plot as a function of dose number and the dissolution number. What you can learn from these plots is that how the change of this parameter would impact the fraction absorbed. So for example, dissolution, it already has a very high dissolution, and therefore if you would further improve the dissolution, it would not result in any kind of increase in the fraction absorbed. So there is no point to work on the dissolution aspect of this formulation. If I look at the dose number aspect, then you can see that even a slight increase in the dose number, which like a slight improvement in dose number, which in this case means a lower dose number, that would result in a fairly big increase in the fraction absorbed. We have all these predictions by keeping one parameter, one of the three fixed, in this case it's permeability. But I can actually change that. And if I change that to dissolution, then the whole plot changes. And you can see now that the dissolution number is kept fixed. And you can assess the same fraction absorbed as a function of the permeability number. And again, the same conclusion can be made as for the dose number, that a slight increase in the permeability number would increase the fraction absorbed dramatically. So now let's look at the same plot for the itraconazole solution. So I make the itraconazole solution prediction active, and I click the FARS view, and yes, and I get the same plot with the same numbers, same predictions, and I will set this one as well to have this dissolution number as the fixed parameter, so I can see the dose number and the permeability numbers. I will close the table format, and I can just click and pull this on the left-hand side. And with that, I can basically split the screen, and I can look at the fraction absorbed rate limiting step prediction for the capsule and for the solution. So what conclusions can we make based on these? You can see here that the rate limiting step was determined as solubility as the water layer permeability, and basically with the Sporanox solution formulation, they managed to improve the dose number aspect of it. So dose number is here 12.7, and it was 18.3. So they improved the dose number, which means they improved the solubility. And they also managed to improve the permeability. It is now 15, and it was 7.6. So they basically have a double in the permeability number. So they managed to improve the formulation from both aspects, from the aspect of solubility and also from the aspect of the unstable water layer permeability aspect. And therefore, the actual formulation went from like roughly 30% of fraction absorbed to up to 80. Yeah, and then this formulation has further advantages as well for the actual patients. So with that, I will ask my colleague to launch the last poll, and I will switch back to the presentation mode, and I would like to thank you for your attention, and I'm happy to answer any questions that you may have.
Thank you, Balint. While we have that poll running, I do have one question here for now on the DPD case study.
Yes.
Could the two particle populations be measured for the powder to confirm the hypotheses, or could these be agglomeration that happen over time?
Yeah, that's a very good question. Unfortunately, for this particular project, we haven't had access to actual proper particle size characterization tools. So these are only hypotheses, and we couldn't really confirm what's the actual phenomena behind it. Do you always need to have encapsulated products, or you can also work with liquid formulations? Yeah, I mean, in the microflux setup, it's actually easier if not the finished dosage form is used, because then a tablet or a capsule needs to be grinded or needs to be somehow. I mean, this dose reduction needs to be done. So yeah, I mean, just like an amorphous dispersion or a solution, those can be easily used in the microflux or in the bio or mini flux setup as well. Yeah, so a capsule or tablet is not a requirement. We did some essays and estimates based on flux results of pure APIs as well. So it don't necessarily even need to be a formulation. It can be just a pure API. Yes, I think if there are no more questions, then we basically got to the end of the session anyway. So thank you very much for your attention, and have a good rest of your day.
Yes, thanks everyone for your time and attention. And if you have any questions, please do feel free to reach out to us. Have a wonderful day. Goodbye.
Bye.